Thanks. It's a pleasure to be here. And everything I'm going to say today is joined with Ty Lidman. I think that's a theme of a few of the talks this week. Great. Okay. So what's our goal? So our goal is to consider the question of when does a four-manifold admit a symplectic structure? So remember, a symplectic structure is just a closed non-degenerate two-form. And so we're going to talk about some obstructions coming from Hagel-Floer homology. So what's the setting? So we're going to be considering closed, oriented, smooth four-manifolds. And we're going to focus on the case of simply connected four-manifolds. Okay. And so the geography problem for symplectic manifolds considers the following question. So which signatures and Euler characteristics can be realized by symplectic four-manifolds? And so remember, the signature of a four-manifold, well, you have the intersection form on H2, and you just take the signature of that form, and that gives you the signature of your manifold. So why might you care about this question? So one reason you might care is if you're interested in exotic four-manifolds. So ones that are, like an exotic R4 is one that's homeomorphic to R4, but not diffeomorphic to this standard R4. So how does the presence of a symplectic structure help us construct an exotic four-manifold? So one example to consider is let X be the K3 surface blown up at a point. And so what features about this space do we care about? We care about the fact that, so this is simply connected, symplectic. It has an odd intersection form. And B2 plus is 3, B2 minus is 20. And so then Friedman's work on topological four-manifolds, well, tells us that this space X is going to be homeomorphic to the to a connect sum of CP2 and CP2 bars. And the exact number is determined by these two numbers. So Friedman tells us that X is homeomorphic to the connect sum of 3 CP2s and 20 CP2 bars. Whereas work of Taub's using Seiberg-Witten invariants tells us that if we have a manifold with B2 plus at least 2, so a manifold with B2 plus at least 2 and a CP2 summand, cannot be symplectic. So in particular, well, this space X, it's homeomorphic to connect sum of CP2 and CP2 bars, but not diffeomorphic. So we've constructed an exotic 3 CP2 connect sum 20 CP2 bars. so, well, what case do we want to consider today? So today we're going to focus on the case where x is positive definite. So that just means that its intersection form is positive definite, and b2 plus is at least 2. So what about an x is positive definite? With b2 plus at least 2. Okay. Well, work of Donaldson combined with Friedman's result tells us that such a space X is homeomorphic to the connect sum of CP2s. And then again, we can apply Tabbs's work to tell us that, well, we know that this can't be symplectic when n is at least 2. So in particular, well, if we had a simply connected positive definite symplectic four-manifold, that'd be an exotic CP2, connect sum of CP2s, and there are none of those which are known. So a simply connected positive definite symplectic four-manifold would be an exotic connect sum of CP2s. And none of these are known. So unfortunately, I'm not going to construct one of these for you. So I'm not going to tell you that there exists an exotic connect sum of CP2s. Instead, what I'm going to tell you is that under mild hypotheses, there are none of these. Okay. So let me tell you what those mild hypotheses are. So we need the following definition. A manifold is geometrically simply connected if it admits a Hagel body decomposition with no one handles. Great. And so here are the following remark. Well, geometrically simply connected implies simply connected. Okay. And so the main result that I want to tell you about today is the following. Let X be a closed, geometrically simply connected four-manifold with B2 plus at least 2. Then if X is positive definite, then X is not symplectic. So that's exactly sort of the next remark I wanted to make. So you might wonder, well, you're wondering like how restrictive is this? So in particular, well, is the reverse implication true? So it's open. That's a Kirby problem. So yeah, so that's exactly what I want to say next, is that this is open for if you care about closed four-manifolds. Okay. What other remarks do I want to make? Say that again?
So what they read as implication, is it something like a topological implication without one handle?
There is no such thing.
Not even in the topical category?
There is no such thing as topological handle. It's like the three manifolds are smooth, so topological doesn't make a difference. They don't admit topological non-smooth commutation.
Great. Okay. And so, right. So the question is open whether you, if a simply connected four-manifold has handle-body decomposition with no one handles, you might not. And so related, you might wonder about 1 and 3 handles. And so let me first give you the following definition. So a perfect Morse function is a Morse function where the number of critical points is equal to the sum of the Betti numbers. So it's sort of like you just have like you have the minimum number of critical points. And so sort of there's a more general question than that backwards arrow there. And so you might wonder if every simply connected four-manifold admits a perfect Morse function. So more generally, you might ask, does every simply connected four-manifold admit a perfect Morse function? Right, so in the case of a simply connected four-manifold, this would be this would give you a handle-body decomposition with no 1 or 3 handles. Great. And so then, I'll just point out that, well, if you were able to find a simply connected positive definite symplectic four-manifold with B2 plus at least 2, well, this would provide such a counterexample. To both of these questions. But as Andras pointed out, no such examples are known. Are there any questions?
So, do you think like such an example? I mean, I assume that your proof kind of relies on having no handles, but is it sort of a technical thing that maybe you could get around, or?
Is it so? We thought about eliminating this hypothesis, and we weren't able to get around it, but maybe that's a failure on our part. And I mean, so I'll sketch a little bit about the idea of the proof. And so the proof really uses that you're starting with a 4-ball and then you're just attaching a 2-handle to that 4-ball. So that's like an important part of the proof. So from that sense, you can't just obviously generalize what we do to have 1 handles. But maybe there's something more clever you could do. Other questions? Right, so the theorem, in the theorem we need B2 plus to be at least 2, but even so we can still use that result to say something about four-manifolds with B2 plus equal to 1. So let me tell you about the following corollary. this is pointed out to us by T.J. Lee. So if X is a simply connected closed four-manifold with positive definite intersection form, a perfect Morse function, and a symplectic structure. Then X is in fact diffeomorphic to CP2. So now let's see how this corollary follows from the theorem. Okay. Well, from the theorem, we have that B2 plus has to equal 1. And so in particular, we know that X has antibody decomposition where we have 1, 0 handle, union, right? So we have a, we know we have this handle-body decomposition since we have a perfect Morse function. So we have a 0 handle, we have a single 2 handle, and we know that it's attached, it's plus 1 frame 2 handle attached along some knot in the 3-sphere. And then we have a single 4 handle. Great. Okay. So we have, there's no 1 or 3 handles. So in particular, so we're starting with the 0 handle, we're attaching this plus 1 frame 2 handle, and then we're capping that off with a 4 ball. So that tells us that, well, once you've attached this plus 1 frame 2 handle, the boundary that we have is plus 1 surgery along K. And so that has to be equal to S3. And so then a result of Gordon and Lukey tells us that K had to actually be the unknot. So in particular, well, this is just the standard handle-body decomposition for CP2. Oh, B2 plus is 1.
Oh, the intersection form.
Yeah, yeah. And that concludes the proof of the corollary. Other questions? Okay, so now I want to say a little bit about how you prove this theorem. And so the proof of this theorem relies on the Hagel-Floer closed four-manifold invariant.
Excuse me, but it's not CP2 has an exotic symplectic structure.
I don't
It's
think.
not. Is that open?
No, it's open. It has a unique structure.
It has unique symplectic. Oh, okay. So it's actually symplectomorphic. Yes.
Yeah, that's a good point. Yes. Proof relies on the Hagel-Floer closed four-manifold invariant, which I'll denote phi sub x comma s. So X is a four-manifold, and S is a spin C structure on X. Okay. So what feature of this invariant do we use? Well, we use the following theorem of Ajroth and Szabo. Which tells us that if X is symplectic, then B2 plus is at least 2. Then this invariant is non-zero for a certain S. So for S, the canonical spin C structure. And this is the Hagel-Floer analog of Taub's theorem. Okay, so let me tell you what this closed four-manifold invariant is. So first, I'm going to tell you a little bit more about Hagel-Floer homology. Nathan sort of introduced it a little bit this morning, but we're going to need a few additional properties of it. Okay. So Hagel-Floer homology is a 3 plus 1 TQFT. So what does that mean? Well, so to a closed three-manifold Y, we associate, so Nathan talked about HF hat this morning. We're going to need the more robust flavors, HF plus and HF minus. And as he mentioned, these groups split along spin C structures. And so what type of algebraic objects are these invariants? Well, these are graded F adjoint U modules. So for us, F will be the field of two elements, and U is a formal variable. Has degree minus 2. And so now if we have a cobordism between two three-manifolds, well, that's going to induce a homomorphism between the respective Hagel-Floer homology groups. So if you have let's say a spin C four-manifold cobordism, so that looks like something like we have a four-manifold W. On one end we see Y1, on the other end we see Y2. And there's spin C structures everywhere, which, if you haven't thought much about Hagel-Floer homology, you can just sort of ignore all the spin C stuff. It's sort of maybe more for the experts. So this is a cobordism between Y1, S1, and Y2, S2. Well, this induces a homomorphism. We'll call it FWS between the Hagel-Floer homology of Y1 and the Hagel-Floer homology of Y2. So I mentioned that we're gonna actually need both flavors of Hagel-Floer homology, both HF plus and HF minus. So let me tell you sort of what these modules look like. So Well, let's focus on the case where Y is a rational homology sphere. Then, well, HF minus of Y has a non-canonical splitting as F adjoined U plus something we'll denote HF red. Where here, HF red is all U torsion. So what does a finitely generated U torsion F adjoined U module look like? Well, it's just going to be the direct sum of some pieces that look like these sort of truncated polynomial rings. Okay. And so HF plus admits a similar non-canonical splitting. So HF plus is going to split as F adjoined U inverse plus the same HF red. So this is the HF red here and here is the same. So there's this relationship between HF minus and HF plus. To see where this relationship comes from, there's an exact triangle relating HF minus, HF plus, and HF infinity. And HF infinity, for any rational homology 3-sphere, this just looks like F adjoined U inverse. And this exact triangle is U equivariant. So in particular, you can see that anything in here that's U torsion gets mapped to 0, because you can't map it into here. So that's sort of, from that you can conclude this. Oh, and maybe to relate this to Nathan's talk this morning, a rational homology sphere is an L space exactly when HF red is 0 in every spin-C structure. So that's sort of another way of saying it has minimal Hagel-Floer homology. This part goes away. So as I said, these invariants are graded F adjoined U modules. I haven't really said much about the grading. So sitting in here, well, you have the element 1 sitting in F adjoined U here, and you might ask, well, what's the grading of 1 sitting in here? So it's going to be some rational number, and that's the D invariant, or Hagel-Floer correction term. So the grading of 1 sitting in here is the D invariant. And the D invariants are invariants of rational homology cobordism. They give a homomorphism from the rational homology cobordism group to the rational numbers. So in particular, the D invariant reverses sign under orientation reversal. Any questions? Okay. So those are sort of some of the features of Hagel-Floer homology. So how are you going to define the closed four-manifold invariant? So let's let X be a closed four-manifold with B2 plus at least 2. Okay. So we can remove 2 four-balls from X to get a cobordism from S3 to itself. So remove 2 four-balls. Okay. And so, well, we're going to have to do a little bit more. So we have this cobordism. We're going to cut it along some 3-manifold N. And we're going to, we want n to be an admissible cut, and so there's some certain, let me tell you what that means. So n is an admissible cut if, okay, well, b2 plus of x is at least 2, and so for n to be admissible, we require that on either side, so let's call these w1 and w2. So we need b2 plus of wi to be at least 1. And there's also this sort of technical condition. So we need delta of h1 of n to be 0 in h2 of w. So let's call this whole thing w. Where here delta is the co-boundary map in the relative Maya-Viatora sequence. So remember, spin C structures are in bijection with H upper 2. So this condition here is just telling us that there's going to be at most one spin C structure on all of W that restricts to a given spin C structure on W1 and W2. Okay. So now, we'll get into defining this closed four-manifold invariant. So we can consider, we have a cobordism from S3 to N. So let's consider the map F minus from HF minus of S3 to HF minus of N. And then we also have this cobordism from N to S3, and we'll consider the map on HF plus there. And now, since b2 plus of wi is at least 1 for I equals 1 and 2, it turns out that this map actually, it factors through HF red of n. And similarly, this map here also factors through HF red. And remember, HF real, it's the same HF red. So if we compose along this way, we get this sort of mixed map, because it's called the mixed map because we're mixing sort of, minus and plus flavors. So F mix is this map from HF minus of S3 to HF plus of S3. And the closed four-manifold is just defined in terms of the vanishing or non-vanishing of this map here. So the four-manifold invariant is 0 if and only if this mixed map is 0. And well, let's say for us, the four-manifold invariant will take values in F. So it's either 0 or non-0. Questions? Okay. Oh, the Manifold thing, it's just like to make sort of the spin-C structures like work out.
Okay.
It's just like you need it to define the four-manifold invariant.
So it doesn't, like, you don't have to put extra conditions on your manifold in order to get this.
No, like sort of, as you'll see, like in the way our proof works, we obviously we're going to cut along some three-manifold, and it just sort of automatically by construction works out that it's an admissible cut. Okay. Other questions? Okay. So recall that the trace of a surgery is this four-manifold Wn. So this is just a four-ball union N-framed two-handle attached along K. And so, and then the boundary of this is N surgery along K. And so the proof of our theorem relies on a sort of technical proposition in terms of the cobordism map associated to the trace of surgery. So if D of +1 surgery along K is 0, and n is some positive integer, then the cobordism map associated to the trace of n surgery along K this is 0 for all spin-C structures. So let me make a couple of remarks. So you might wonder, well, how common is it for D of +1 surgery to be 0? And so let me just give you several classes of knots for which this is true. So examples of knots with D of +1 surgery equal to 0. Well, this includes all slice knots. So remember, a knot is slice if it bounds a smooth disk in a properly embedded smooth disk in the four-ball, whose boundary is your knot sitting in the boundary of your four-ball. Negative torus knots also have this property. More generally, any knot with a negative L-space surgery so any knot in which you can do some negative surgery and get an L-space. And then also alternating knots with positive signature. So for the experts in the audience, let me just say a few words about how this proposition is proved. So we proved this proposition using the Ajval-Szabo mapping cone formula. So the mapping cone formula gives a way to calculate the Hagel-Floer homology of surgery along your knot in terms of certain maps on the knot-Floer homology of K. So this mapping cone formula, not only does it give you a way to compute the Hagel-Floer homology of surgery, but it also gives you a way to compute this map. And the fact that d of +1 surgery is 0, well, that tells you that certain maps in the mapping cone are going to be surjective. And then the idea is that this cobordism map is determined by the inclusion of some subcomplex into the mapping cone. And then, well, if the map is surjective onto the thing you're including, well, then the map's going to be 0 when you take the homology of the mapping cone. So the idea is that if d of +1 surgery is 0, certain maps in the Adler-Szabo mapping cone are surjective. So now, let me show you how the theorem follows from this proposition. So the first step is that, well, if you have a four-manifold X that satisfies the hypotheses of the theorem, so simply connected, geometrically simply connected, positive definite, B2 plus at least 2. So X, as in the theorem, well, it has a handle body. Decomposition with no one handles, and the linking matrix for the two handles looks like, so there's going to be a block that looks like the identity, and then everywhere else is 0. Wait. Okay. So X has no one handle, so this means that, well, we can build X. We start with a 4-ball, and then we're attaching just a bunch of +1 framed 2 handles along some link in the boundary. So here's X. And so now, well, let's consider we're building this manifold X up. And so let's, we start with the 4-ball, and then let's attach our first 2 handle along some knot. It's going to be +1 frame 2 handle. So let's build it up this way. So sort of at the first step, what are we going to see? Well, here on the boundary, we'll see +1 surgery along some knot K, just whatever, pick some first component in your link. Here is going to be the trace of that surgery. And then here is just whatever, this is just whatever is left. Okay. So, this is, sorry, trace of 1. Okay. B2 plus of W1 is 1. Right, so we want to, so what's the idea of the proof? We're going to show that the four-manifold invariant is 0. So this is going to, we want to show this is an admissible cut. Wait. So, well, B2 plus of P is just going to be B2 plus of X minus 1. B2 plus of X is at least 2. So this is at least 1. And, well, this is an integer homology sphere, so that homological condition is automatically satisfied. So in particular, this gives us an admissible cut. plus 1 surgery along K, well, this bounds the trace. This is positive definite. And so it's a property of the Hagel-Floer D invariants that if you bound something that's positive definite, well then your D invariant is non-positive. But now, well, we also have, looking at in the other direction, we have that minus this surgery bounds P, which is also positive definite. So this tells us that D of minus this surgery is also non-positive. So since D invariants reverse sign under orientation reversal, well, this tells us that D of plus 1 surgery along K is 0. Great. So now, well, now we can apply this proposition. So this tells us that this map F minus is 0 for all spin C structures. And now, remember, well, this coordinate map is sort of the first step in the definition of the mixed map. So if we show, well, the first map is 0, then the whole map is 0. And so, well, if the mixed map is 0, then the four-manifold invariant is 0. So that basically does it. So now, apply the proposition. This tells us that F minus is 0. And so then from the definition of the four-manifold invariant, we get that that's 0 as well. Oh, and this, the proposition was for all spin C structures. So this is for all spin C structures. Questions? Oh, so yeah, we don't use n bigger than 1 in this proposition, but we prove it more generally because of the next theorem I was going to tell you about. Yeah, so here we just use n equals 1. So thanks. That's a perfect segue into the next thing I want to tell you, which is the following theorem. All right. So let K be a knot with D of plus 1 surgery equal to 0. So, for example, any of those knots. Then, for n bigger than 0, and any contact structure on the surgery, the trace cannot be a symplectic filling. For your surgery. Great, so let me sketch the proof. Okay, so we'll prove this by contradiction. So if the trace symplectically fills the surgery, then it turns out that the trace embeds in a symplectic manifold X with B2 plus at least 2. This is a result of Etnayer and independently Eliashberg. Okay. So now maybe it's apparent how we can use this proposition to prove the result. So we have X. The trace embeds. Wait. And so now, well, if we just consider the four-manifold invariant for X, well, here let's just look at this cobordism from S3 to the surgery, and now we can apply the proposition for any positive n, and we're going to see, well, this map here has to be 0 for all spin C structures, so the four-manifold invariant is going to be 0. The proposition, well, implies this is 0, which is a contradiction.